Fantastic. So our next presentation is on computational pathology with Dr. Bertram and Professor Aubreville. Professor Aubreville received his Master's of Science in Electrical Engineering and Information Technology from Karlsruhe Institute of Technology in 2009. Following several years as a developer and systems architect in research and development of medical devices, he joined the pattern recognition lab part-time at Friedrich Alexander University Langen, Nuremberg in 2016, where he completed his PhD in the field of deep learning-based tumor diagnosis with distinction in 2020. In October 2020, he was appointed as a tenured professor at Technische Hochschule Ingolstadt in the field of image understanding and medical applications of artificial intelligence. I'd like to welcome Dr. Bertram and Professor Aubreville with computational pathology.
Thank you very much for this kind introduction. So Professor Aubreville will not be here today, unfortunately, but he prepared a video for us, so he can still contribute to this talk. And so we'll check whether we can hear the video via Zoom. So here's a short welcome note, and please let me know if you can hear us.
Warm welcome from my side. My name is Marco Preville and I'm a professor of computer sciences. I'm working at Ingolstadt Technical.
It's very quiet. Maybe can the volume be increased a little?
Yes, I'm trying. Hang on. What about this?
And also a very warm welcome from my side. My name is Marco Preville and I'm a professor of computer sciences.
Okay,
I'm
great.
working at Ingolstadt Technical University of Applied Sciences, or Technische Hochschule Ingolstadt as the proper German name for that institution is. It's a small or medium-sized university in Ingolstadt in Bavaria, Germany. I've been working in the field of computational pathology, especially veterinary computational pathology, for quite a while now, and I hope that you can all live with me being in this white void at the moment, because actually I'm now on holiday, so yeah, still hope that we have a great time together.
All right, great. So that should work. So yeah, so Mark and I did work quite a bit on computational pathology for veterinary medicine in specific. And him and some other co-authors, especially Professor Kopfleisch, was a huge contributors to our work that we did. And as this whole group, we developed guidelines for computational pathology. So there was earlier today, there was a comment in the link that said AI will lead itself to a lot of standardization and need to be included in this venture. So that's a quote from a participant today. And so this is the purpose why we decided to do a guideline on computational pathology, because it is a pretty it's a tool with a lot of promise that we can standardize our parameters. We all know that we as pathologists have limitations, and Rebecca just earlier told about many parameters and mentioned commonly mentioned limitations by pathologists. And computational pathology certainly is a method where we can try to increase or reduce that limitations. So we consider this as a potential method for future. It's not currently not included in tumor prognostication as a routine method at all, but it is certainly a promising method for future. So we decided to already start with some guidelines, and it's the guideline that you can also find on our website is still quite minimal. So we have some general aspects, and we have added specific aspects for some prognostic parameters, those that we have some knowledge on, and this will hopefully increase in the future, and we will have some guidelines for specific parameters in the future. So for now, we mainly have specific guidelines for metodic figures and some immunohistochemistry assessment. So this talk will include a short introduction and some examples, so everyone just get a short feeling what computational pathology can do for us as pathologists and as tumor pathologists. And then the video from Mark will give a basic introduction to AI. And then I will continue to talk about the role of pathologists for computational pathology in developing those algorithms and also in application in the future. And then if we have time, we will talk about 2 examples of application. Right, so computational pathology, and specifically, we're going to talk about automated image analysis. Computational pathology is a little bit broader in its use, and our guideline right now is just talking about automated image analysis. So automated image analysis has especially become interesting since we have the technical equipment to digitalize our slides routinely. So certainly, obviously, you need images to do image analysis. And whereas you could take pictures, this would be just adding a step to your workflow. And when you have digital workflow anyways, this is just increasing the interest for automated image analysis. So digital images can be analyzed by pathologists, as we do routinely, and can be analyzed by algorithms, which is called automated image analysis. And by using algorithms, we hope to, well, we're definitely going to increase reproducibility because algorithms are by nature reproducible, 100%. And ideally, would also increase our accuracy of the analysis and potentially the efficiency of the analysis. So any of those advantages would be the goal when using automated image analysis. And thereby we can increase our prognostic capabilities in labs. But automated image analysis isn't a solitary thing. So there should be, at least at this stage, interaction with pathologists. So combining those two would probably be the goal for at least next years. This is called computer-assisted diagnosis or computer-assisted prognosis, and we're going to talk about this in a little bit. So we have broken down the algorithmic approaches into 2 big or 3 big approaches. So the first is probably an approach that's quite commonly known for many pathologists, as it has been used for a rather long time, or comparably a long time in literature, mainly as a research tool. So that is using thresholding algorithm or algorithms that you can manually adjust. And there's many algorithms commercially available or even open source available that can be used. So this is rather a simple algorithm where you just use program filters, and an example would be analysis of Ki67. So there's an image, I think it was a mast cell tumor stained with Ki67, and you can use this default algorithm and modify the parameters in a way that it is analyzing the image with high accuracy. So you can, for example, you have, so the nuclei are segmented. So this is other round circles, other nuclei that are segmented, and you can modify the parameter for segmentation. So here in the middle is probably the best ideal set of parameters for segmentation. Here you have a little bit of under segmentation where you don't detect all tumor nuclei, and here's over segmentation where you, the nuclei are not distinguished well enough. And then you can also modify the parameters, the thresholds for classifying those nuclei into low staining and labeling intensity, moderate staining intensity, and high staining labeling intensity. So those are parameters that can be modified manually by the user, and in order to adapt those algorithms. And this is, those algorithms aren't very they aren't able to detect or analyze difficult patterns. So those algorithms are mostly used for immunohistochemistry. And there's plenty of studies, especially in human medicine, where they have shown that this can actually lead to a higher prognostic value of the parameter when they are assessed in a more reproducible and actually also more accurate way. So and then there's data-driven algorithms, which are more or less synonymous with with AI, artificial intelligence. And this is going to be the main topic of this talk. So we're going to talk about machine learning in specific, and there's traditional machine learning methods, and there's deep learning, which is a subset of machine learning with more complicated, more deep models. And Mark is going to give a little bit more detail about this. But generally, we have a model. It's a neural network, especially in the sense of deep learning. And we can pre-process images, which are simple filters. We can post-process images, and the hardcore of the algorithm is the model. And the difference is that traditional machine learning, we do have to extract features as a programmer and give that features to the algorithm, whereas the model is deeper with deep learning, and they are able to extract those features by itself and thereby have higher power to find statistically relevant features in the images. So data-driven algorithms generally are more powerful, and they can analyze or detect more complicated patterns than the thresholding algorithms. And here's just some examples that I picked for this purpose. There's a little bit longer list on the guidelines. So those are parameters that have been evaluated in research studies, mainly for human medicine, but there's also a few for veterinary medicine. And the field of application is actually quite wide. So there's more or less nothing that you can't imagine can't be done by AI algorithms. And we classified the task for the algorithm into classification, object detection, and segmentation. And Mark is going to give you more details about this. And we have classified the pattern of interest to different dimensions of magnification of structures, which is a cellular structure, a structural pattern, and a global pattern. And you have, for each of those, you have different examples. A very popular example is metotic figures. And our research group actually has been doing quite a bit some work for canine mast cell tumors and also for canine mammary carcinomas for detecting metotic figures. And we were able to achieve some impressive results. And we're also going to talk a little bit about this later. So this is the algorithm detecting metotic figures and visualizing the detections by a green square along with a confidence score in canine mast cell tumors. And here's another work from our research group where we detected tumor cells with 2 or more nuclei, so binucleated tumor cells or multinucleated tumor cells, which is, as you all know, a parameter for canine cutaneous mast cell tumors. The algorithm wasn't just as good as for metotic figures, but still was able to reach performance of pathologists in detecting those structures. And the next 2 examples are from human medicine. So we don't have studies yet, as far as I know, for veterinary patients. But a topic of interest in human medicine is detecting metastasis in lymph nodes in breast cancer. And the reason probably for one is that there is a big data set publicly available. And there was a challenge where they developed algorithms for this task. And the availability of this data, of course, makes it possible for many research groups to use this and work on improve algorithms. So the task was to segment or find areas of metastasis in lymph nodes. And in this example, this probably might be very easy. And then all of you will see this at low magnification that there is metastasis in this lymph node. This is a breast cancer metastasis of a dog, not of a human. So it's my own pictures. And the analysis of the algorithm could look similar like this, where they just highlight the areas. And we're also going to talk a little bit about this when we talk about examples. Another example would be to detect or analyze or classify tumor malignancy. So there's also a challenge in a publicly available data set for human breast cancer. And the task was to classify whether this image, so they had medium magnification images of this tumor, and the task was to classify this as normal breast tissue, benign tumor, in situ carcinoma, invasive carcinoma. And they were also able to algorithms, or the best algorithm that developed for this challenge was able to score as high as pathologists were able to classify these images. So, this images were supposed to show you how powerful those algorithms can be and what they can analyze. But it's certainly not that easy. So from going from this input image, so having this metotic figure and probably not metotic figure, classify these as 2 different structures and distinguish those is very complex and difficult. And there's a long path to go to develop those algorithms. And while we develop those, you will get across a lot of definitions and rules and new stuff that we probably, as a profession, will be using in the future quite a bit more. and Mark will give you quite a short introduction to the basics of what we are going to talk about.
In my research, I'm using methods of artificial intelligence. And while some might think that this is magic, I can assure you that it's not. So let's look into this now. One method of AI is called machine learning, and that's also not too complicated to understand, and that's why we'll also talk about it now. The guiding principle behind machine learning is nothing more than an algorithm is trying to mimic an observation made in the real world. So what does that mean? So typically we have some input data. Let's be very abstract here. We have some real world process and we have some observed output data. So what do I mean by that? I give you an example. We have, for example, the input image, which might be an H&E stained tumor image of some kind, or just a subfraction of that. Then we have, for instance, a pathologist that looks at that image and says, oh, well, that's for me a high-grade canine cutaneous mast cell tumor, for example. That's our observed output data. Okay, so we have input data is the image, we have the pathologist, which is mimicking or which is actually doing the real world process, and then we have the observed output data. Right, let's move on. The observed output data is often also denominated as observations, or in the scope of an algorithm as training data. So this is something where the algorithm can learn from, can try to mimic this real world process. So what is then done in the model training, how we call that, is that we replace kind of the real world process, or we try to mimic the real world process by a machine learning algorithm. So in that way, it tries to mimic in the best way possible the input data towards the similar predicted output data. So after we have managed to do that, and after our machine learning algorithm has been trained, how do we know we did a good job? One could assume that the easiest thing is to say, well, let's just feed the same input data and see if the predicted output data is exactly what we expected. So that is equal to the observed output data, right? Well, not quite. But why is that? Well, today's algorithms are extremely good at memorizing something. So that means only because we have seen that it works fine with the training input data that we've given to the algorithm once, it doesn't mean that on independent other input data it works as well. It might have been that the algorithm has just learned the relation between input data and output data by heart and does not generalize. So how do we get around this issue, and how do we really test that our data set really works also on unseen data? We do that typically if we only have one data set. Let's assume that this is our data set now, this big white box is our data set, by subdividing it into three parts. The test part, the validation part, and the training part, or in the other way round, right? The other order. What is it that I'm talking about? So the training part is used to really tune all the little weights of the algorithm so that we can mimic input to output data with the algorithm. That's usually at least the biggest chunk. I say usually because that really also depends on if you have a sufficient amount of data. If you have a large amount of data, then you can keep the training set also moderately to not at least the biggest chunk. Then we have the validation set. The validation set is used in order to control for the training process. So that means while the training is ongoing, it's an iterative thing, an iterative process, we will want to check how well do we do. So that's our validation set. Finally, we have a holdout set. And the holdout set or test set is the one that we use only once and only at the very end in order to see how does the algorithm now perform on really unseen data. So now we have three data sets or three dataset parts, and we could say, wow, that's cool. Now we can evaluate and find the real truth about how well our algorithm performs. Still, we have to be very cautious about what we're doing here, because there's the devil's in the detail when doing this dataset split. And in fact, many, even in the very recent literature, are doing it blatantly wrong. So when you do the split, you have to make sure that these datasets are really qualified as independent. What does that mean? I'll give you some examples of when it's not independent. So, for example, you could say, let's take some parts, some image crops, some image patches, as we call them, from a whole slide image. We have, for example, 2 whole slide images. We take crops, and then we randomly assign these crops into training, validation, and test set. Now, these are not independent anymore because they belong to the same 2 whole slide images. So that means that we have something that they share, and this shall not be the case. They need to be independent, so they do not, we do not allow them to have a common prior. Then they also need to be representative, which is also debatable for 2 whole slide images, right? So we need to have a selection, especially for the test set, that is really representative of the actual use case that we're following, and it needs to be completely independent. So that means that in the case of pathology, we need different patients that we use, or different cases, tumor cases, that we use for the training and the test set, and ideally also for the validation set. And even then, it's actually not the ideal scenario, because ideally we would also use different labs, different scanners for the training and the test set. Only then we can really say that what we trained the algorithm on will really also work out. Of course, we could say this algorithm we want only to work on the images from our lab, so we only need to test it on our lab. That's perfectly okay. But of course, then you have limited conclusions on what or how well your algorithm generalizes. In machine learning, especially in machine learning on images, we discriminate 4 different tasks that I want to talk to you about. First up, we have classification. That means that we assign a label, be it cat, to an image. Here in this case, it's the image with a cat on it. So that means that we do not differentiate between what's within the image. We just say, okay, this image is cat. Could also be that this crop out patch is mammary carcinoma. Then we have segmentation. Segmentation means that we assign each pixel of the image with a class. So in this case, all the pixels that correspond to the cat have been labeled the class of cat. Third, we have object detection and classification, or also short, just object detection. In this case, we want to find typically the bounding boxes, which are the ones that you see here, that give us an implication about where an object is located and of which class it is. So you see here, for example, the cat, the chair, and the glass. And finally, we have a combination of object detection and segmentation, which is instance segmentation. So in this case, also overlaying instances are being separated and discriminated, and also assigned with a class, and we assign to each of the pixels one of those instances. When we're doing machine learning on images, we will typically not feed the image directly to such a machine learning model, but we would do first a pre-processing, for example, to reduce noise. We will do a feature extraction to extract meaningful, sensible information from that image. And then we will run a machine learning model and get an output. For example, a classification or maybe also in this case a segmentation. Now, what can you imagine such a feature to be like? So as an example here, I have taken a task from Tumour grading. So here, for example, we could have the two features that correspond to each other. So one, the mitotic count that was maybe for some reason somehow extracted from the image. And then we have, for example, nuclear pleomorphism in whatever unit that might be. And in this case, the task of the algorithm is to differentiate based on mitotic count and nuclear pleomorphism. So based on those two features, a label which might be low grade or high grade. So in this case, this is a classification task. Well, and in this case, you would see, well, maybe we could just draw a line as some kind of boundary through that image and we're good. Now, of course, this is an easy case and it's only two features. But of course, reality is much more complex. So in order to solve this problem, people in the last decades have invented so many different algorithmic solutions to solve more or less the same problem. So if you hear about support vector machine, decision tree, random forest, even maybe a linear regression, to name the most simple of all, these are just examples of machine learning approaches that have been used widely in the past. And thus, more recently, machine learning or classical machine learning has gotten a very powerful sibling, and that's deep learning. So the main difference between classical machine learning and deep learning, besides that deep learning is commonly done using a special kind of machine learning, which is a neural network, is that in the case of deep learning, we do not have this whole processing chain of preprocessing, feature extraction anymore, but we have only one unified, big, fat, complex model to do the whole job. Now, where there's light, there's also shadow, and deep learning has been criticized a lot for delivering black box approaches. So that means that there's an approach that we cannot really look into anymore. Well, that's also not really true, because yes, we can look into it. There's nothing hidden within this model, but it's just so complex that we don't understand it anymore. On the other hand, this has come with really performing or really well-performing models that severely exceeded the performance of previous generations. However, when dealing with such systems, and many people are doing that nowadays, we should always have in mind that what those systems find is a perfectly or almost perfectly correlating input versus output. So that also means that we need to really be careful about our data. We should always have in mind that spurious correlations within the data can mislead the system dramatically. One very educating example was published by Zech and colleagues in +1. They had the task and said, well, we take so many chest X-ray images in our hospitals. Why don't we just use a machine learning system in order to find out if a patient will later on go to the ICU? So they used images of patients, X-ray images, and trained a machine learning system on that. And of course, they also had normal, regular X-ray images taken from the radiology department. And then they had X-ray images from a machine in the ICU, I believe it was. And when they used that, they found out that their system really works well. This is what we see here in the upper, in the upper graph. So this is an AUC curve where we here see, ROC curve, where we really can see that they had a really nice predictive performance. So they could now then go ahead and say, you know what, let's check, like radiation aside, let's just take from every incoming patient a radiograph, and then we know if they end up in the ICU or not. Would be perfect, right? Well, then they did a test on an independent set from another hospital. And that's when they found out that it really broke down dramatically. The performance really crumpled. And of course, they asked themselves the question, so why is that? Now, they used methods that are nowadays often seen as explainable artificial intelligence, And what they did with them is they looked where would the neural network, in this case, look for the decision. And this was really interesting and educative because they found out that the network typically looks at the, what is it here now, upper left part of the image to predict the disease. So they use the site indicator to predict the disease. Well, that is at first really puzzling, isn't it? Why would you be able to use the site indicator? But then later on, they quickly found out why it is, because the site indicator was different. It was different letter in the ICU X-ray machine than in the radiology department X-ray machine. And that means that what the network learned to predict was not if the patient will be in the ICU or not. What the network learned to predict was, is this image coming from the machine in the ICU or from the machine in the radiology department? So that's why you should always be careful about data and what it might also imply. Now, with all that in mind, let's go back to the different machine learning tasks that we can apply on an image. And let's ask ourselves the question, how can we apply this in the world of pathology? Now, I can also say here that, well, it really depends, because there's different ways of framing a machine learning task on a pathology image. As an example, let's have a look at structural patterns. Structural patterns, for example, could be the question, well, is this a tumor or not? This could be either perceived as a classification on the whole image, or maybe even as a classification on subparts of the image. So then we receive the information if this is part of a tumor, this subpart is part of a tumor. Also, we could say it's an object detection task, so we want to detect such a bounding box of the tumor within the microscopy image. Or even we could say it's a segmentation task because we want to detect the outline maybe of the tumor, or we want to see which part of the tissue is predicted to be tumor. Another example could be cellular patterns. There again, for example, mitosis, we could frame this as a classification task, maybe an image with a cell in the very center, and we could ask, is this cell in the center a mitosis or not? Then it would be a classification task with two classes, non-mitosis or mitosis. Then we could say it's an object detection task, and actually in our work this is mostly what we do. So the task is, this is an image, please tell me where you find a cell of a certain class, maybe the class being mitosis. And then finally we could also do a segmentation task where we want to see, okay, I want to have the outline of those cells. Another important term that I want to talk to you about is the term of overfitting and also the term of underfitting. Now, our current deep learning models, they have a vast amount of parameters and they can really almost learn all data by heart. As I said, learning is, however, an iterative process. So that means that in the beginning, when a model is being trained, and it's usually trained on a big machine with a big graphics card, then this model will not do a good job at recognizing the training data. Now, while over time it gets better, initially we call this an underfit. Now let me click here. So we call this an underfit. Over time, however, the model gets better. That means that it will really learn the training set much better. And then at a point, the model will reach a state of overfitting. And that means that it has really mastered now the training set. However, the generalization suffers. So that means that while the performance on the training set gets better and better and better, the performance on the test set gets worse and worse and worse, and also on the validation set. So as I said, the test set we cannot use during this training, but we can use the validation set. And that's also the strategy that is commonly used. So while training, we will observe the performance on the validation set and see if the performance on the validation set also improves. And as soon as the performance on the validation model does no longer improve, we will stop the training process, because everything else would mean that the performance on the validation set will then next deteriorate usually, and we run into an overfit. Now you might ask yourself, why am I talking about overfit and underfit, which is a fairly basic thing, only when I'm already in the part of my talk when I'm talking about applications? Well, because this is not something that is only part of, well, the training process, but you can also overfit to your data set. And that means because the validation set is part of the data set, and the validation set might not be sufficiently independent, then you still run into an overfit. So one of my take-home messages for today would be, well, certainly in machine learning, it's all about the data. And the person that does machine learning but didn't understand the data does a bad job. That's as easy as that. Also, that means that curating the data set is really a big challenge, and it's worth putting effort into it. We know that doing big data sets requires a lot of time, requires a lot of hours to sit there and do sometimes stupid jobs. However, if you want to generate really good results, this is the way to go. And with that, I can hand over again to Christoph and see what he wants to tell us about that.
All right, so that was the introduction into artificial intelligence, and we're going now into the role of pathology. So how can we contribute to this development? And I mean, this is supposed to help us, so we have to contribute to this, certainly. So in this graph, I have summarized the different steps that Mark have also talked about. So, and then on the bottom you can see the role of pathologists and computer scientists at these different steps, whereas lighter color means, you know, higher involvement. And there's certainly some software where pathologists can use, and they can train their own algorithms, but they are generally restricted to very default models and default approaches. So it's generally advisable to team up with a computer scientist if you want to develop high performance algorithms, especially for very difficult tasks such as Metatotic figures. So the input of a computer scientist and the expertise in developing those algorithms, not from a commercial software, is very valuable for a difficult pattern at least. So the first thing would be you have to decide, or have to have an idea what you want to use this algorithm for. So as I said in the introduction, usually you want to use algorithms for either increasing reproducibility, accuracy, or efficiency. And this might depend quite on the specific task, a specific prognostic parameter in this context. So you have to define a way how you want to use those algorithms. And based on this, you develop data sets. So you use images, and generally you need annotations, labels for those patterns that you want to use if you use supervised learning, which is the most common approach for pathology images, as opposed to unsupervised learning, which, as far as I know, have not been commonly used for our field. And Mark talked about the distinguishing the data set into a training data set, into a test data set, the training data set. And this definition contains the validation data set, which is, however, a separate part of this. And this step is mostly done by pathologists. So computer scientists need to help us, need to tell us what they need later on for the training. But the labeling, that's our expertise. We know the definitions, how Metatotic figure looks like. That's nothing a computer scientist knows. So we need expertise to classify these patterns. And this is usually very time consuming, but it's very important, as Mark just said, for training good models. And we're going to talk about this a little bit later. The third step would be training this model. And state of the art usually is deep learning. So you're using convolutional neural networks. And within this step, we as pathologists can contribute only little. So this is mainly the expertise of computer scientists. But at the end, we want to evaluate algorithms using this test data set. And again, this is a step where we actually both need to contribute. We know what we expect from this algorithm. We know how good it needs to be. We know the potential limitations for this task. We know the difficult cases. So we need to contribute just as pattern computer scientists who know the statistic evaluation methods. And at the end, when you have developed an algorithm, of course, you want to implement and use it. Well, at least that's the long-term goal. You want to use it in a clinical situation as you want to support pathologists, and you need to figure out how this is done most ideally. And we're going to talk about this also. So again, Mark said there's the model itself is often considered a black box. So we don't have or know the decision criteria of the algorithm. It's not like Tareen just explained to you how a metatic figure looks like. You need to look for spikes and all that. It's not like that we can get this information from the model because it's just too complex. So it's difficult to see how good it's working, and you really do need good data sets, good test data sets for this purpose. So we're going to talk about this. Right. So why do we want to use AI? And as I said, at least for now, we don't think that AI should be a solitary approach for analyzing. I think it should be coupled with an expert review, so a computer-assisted prognosis, a computer-assisted diagnosis. So the way AI can help us is by addressing our limitations. And we, as I said, we know that pathologists have limitations. We are good at certain things. We're very good at giving a diagnosis, for example, inflammation versus neoplasia. We're very good with that. We're very good with adapting on a specific case. We're very good when we see necrosis or when we see tissue artifacts. We're very good to say, okay, I'm not certain. I maybe my prognosis is not very accurate. So we're good with that. We're good with interpretation of results. But we have limitations, especially for quantification, for counting. We have variability when parameters are not completely clearly defined, which commonly they are not because it's difficult. And especially for those tasks, algorithms have advantages. So they're always reproducible. They can analyze entire whole set images within reasonable time. But of course, they also have limitations, and those limitations need to be handled and reviewed by an expert in order to ensure that the prognosis at the end is correct. And one limitation, and Mark addressed this, of algorithm is robustness. So just because you have evaluated an algorithm in lab A doesn't mean that it works perfectly in lab B. So you have differences in images, and this is going to cause problems for your algorithm. So there are certainly many sources of errors for algorithms, although they're very powerful. All right, so probably the most important thing where pathologists can contribute is developing data sets. And here's our good 2 cents for good data sets. As we said, they are very time consuming to develop. It's very difficult and can be quite frustrating to get this right, but it's very important for your algorithm. And this is probably also the biggest limitation that we currently face. If you don't have data sets, you can't develop algorithms. And if you don't have large enough data sets, the algorithm won't be good enough. And if you don't include enough variability, your algorithm will not generalize for different labs. So this is important. And probably the biggest limitation that we're still facing, and we need to work on this. And we as pathologists, we can develop those algorithms, and we should be doing this if we want AI to be supporting us in our future. So one aspect for data sets is that you need to have images. This could either be whole set images or crop out images of certain regions, depending on what you want to have. So if you want to have analysis of whole set images, this should be certainly preferred. Although like larger images, more annotation work, obviously. And they need to be representative for the intended use. And Mark did give an example from the radiology field. Here's an example for our field, for example. So for us, this is obviously not a metotic figure, because metotic figures cannot be green. They are blue. They stain with hematoxylin. And so that for us, that's easy. We can exclude a metotic figure because it's the wrong color, but that's not how algorithms work. They don't exclude that, they learn from data. And if they haven't learned, so this blue color comes from tissue inking, right? So, and if you train an algorithm with images that have not been inked with tissue color and doesn't contain this green color, it won't be able to distinguish this from a blue metotic figure. So for them, it kind of looks like this. They don't know blue color, green color, sorry. So this was a real life example from one of our mammary carcinoma data sets where we had in the training set this tissue ink. So if you want to have images with tissue ink, you need to include this in your training set, and your algorithm will perfectly be able to distinguish this from a metotic figure. The second step is annotation. So you need annotations for the training and for the testing. And the annotations need to be appropriate so that your computer scientists can work with them, and they need to have the appropriate format and appropriate shape. So that is by using appropriate software, and you need to talk to your computer scientists or use specialized software for that. Then you also need sufficient quantity of labels, so high enough numbers. You need highest possible quality of labels. And we're going to talk about this quite extensively. So annotation software, there's many open source software like this one that Mark has developed for our purposes specifically. So everyone who's interested can download this software. There's further open source software, there's commercial software. Some software even allows to train some models. Okay, so the next thing would be quantity of labels. And Mark has said that deep learning is very powerful, much more powerful than its sibling traditional machine learning, which is true for, I think, probably all examples. But it needs more labels, more images, more examples for training. Because it needs to extract the features by itself. It doesn't know the feature from the programmer, it needs to extract itself, so it needs more input. And this is an example from our algorithm for metotic figures. You can see that the algorithm performance, as given by the F1 score, increases with higher image size, 5 power fields, 10 power fields, and this, of course, corresponds to higher number of metotic figure labels. So the more labels, the larger images you include for training, the better your algorithm gets. And this is actually quite an extensive increase of your performance. Right, so concerning the quality, we need to define two definitions, one of which is ground truth. So the ground truth is the information for the label saying what's the truth based on the gold standard method. So this is not necessarily the true biological truth, but this is what we define as the truth. And this is used for training the models, but also for testing the model's performance. So that's very, very important that it is the ground truth is actually as accurate to the real biological truth as possible. And this gold standard method is the method that we use to develop those ground truth labels. And usually for histological images, we want to label certain structures and morphologies, and this needs to be done by pathologists. And we have talked a couple of times about how well pathologists perform, for example, during the metotic count talk. And we know they are not perfect. And Franke Effner, for example, published recently a very interesting paper where she's discussing all the biases that BS pathologists have, and these biases will influence the quality of the data. So the most simple way to develop a data set would be to have images, to have a pathologist, have them label it with the appropriate software, and then you get a data set. The question really is, do we get best quality data? And well, the answer obviously is no. It could be good enough, but depending on the difficulty of the pattern, there might be significant errors that will also affect the algorithm. So here's an example from our data set that we developed on B and multinucleated tumor cells. The task was we asked 6 pathologists to annotate B and multinucleated tumor cells in an area of 2.37 square millimeter. And here you can see the number of annotations that had consensus by 1, 2, 3, 4, 5, or 6 pathologists. So there's very few structures actually that were labeled by all 6 pathologists. So all 6 pathologists only agreed on a very small percentage of structures, whereas there were many structures that were only labeled by 1 of the 6 pathologists. And here's the images corresponding to those the level of agreement. And you can see the structures that are quite obvious were labeled by all pathologists, but there are many structures that simply are difficult. And for those structures, you won't find easy consensus, but you need to label all of the structures. We need to create data sets, because if you don't label the structure, you automatically say it's a negative. So you always label something, and structures that you don't label, it's a negative example. So it's very important. You can't ignore something uncertain just because you're uncertain, because then you automatically say it's a negative example. So there's different ways to increase the quality or to develop high quality data sets. So the first step is develop data sets by annotators, by pathologists. And this always is the first step. And you can increase the quality by repeated screening. So to avoid that you overlook certain percentage of structures, you can add multiple annotators. So this is always necessary. But as we have said, there is some bias, there is some variability, and this is quite time consuming. And then you can have additional methods for increasing the quality. There's either, or increasing the data set is either for increasing the quality or increasing the quantity, but they're based on algorithms developed from this first data set. So improving the quality can be done by detecting missed candidates. And of course, those are always reviewed by pathologists to ensure the accuracy of these annotations. This can be done by visualization, comparing difficult structures in a certain map. So in this step, you add an algorithm as a support for the pathologist, but you always have the pathologist to give the final decision. But of course, there can be some bias to the pathologist, such as a confirmation bias. You can also create new labels from previously unseen images. This is to tackle the high time investment for the pure annotator task. But this will also have some bias. But it is commonly done because creating data sets are very, very expensive and time consuming. And then there's the fourth possibility where you simply use an algorithm to predict labels, new labels, without review by pathologists. And this is not recommended by our group, and especially not recommended for training data sets. So this is a no-go for training, for evaluation. Those are sometimes done for small data sets where they don't have pathologists to annotate more images. And I think we as a profession should be willing to contribute in order to supply large enough data sets so that the computer scientists don't have to use this poor trick. So instead of using this simple approach for labeling, our research group, for example, has been using this approach. And this was especially used for the Metatotic figure data set in canine mammary carcinomas. So it's much more complicated, obviously much more time consuming, but at the end it was much more accurate. And we compared the different steps, the different algorithmic or data set steps, compared the performance of the algorithms derived from those, and we could see that the algorithmic performance was much higher. So we repeated the screening process. We had a second annotator to confirm the label, and if there was disagreement with the third pathologist to give the final decision. And then we added algorithms. So those are just examples what you could do. Depending on the pattern, this might be a little bit different. But for Metatotic figures, we do know that pathologists, and specifically I was the first person, so also I overlooked quite a high percentage of Metatotic figures, even when screening twice. So we added an algorithmic detection of Metatotic figures, but they were reviewed by pathologists, and we had a high sensitivity and those specificity. So we had many false positives that we had to exclude here. So we reduced the confirmation bias. Same thing, confirmation by pathologists. And at the end, then we also had a visualization of the mitotic figures versus lookalike. So right at the border of those two colors, they are the very difficult mitotic figures. And this was done for consistency. So anything at the end of those tells based on the algorithm should not be consistent, and we could verify those and get more consistency in the data set. So all those steps intended to improve the quality of the data set with success, but very much high time investment. Okay, so the third step would be training of the model, and this is not where we get to do a lot of things. This is done by the computer scientists generally. But again, it's nice to see how the data set comes into play. So we create a data set, and the data set is used for training. We have a validation data set that uses to evaluate the training process. And then at the end, we test the model with a separate test set. So this is very important for all steps of the development of the algorithm to have a valid and good data set. Okay, so then again, evaluation, very important step for seeing how well the algorithm performs, because it is a black box. We don't know how it decides what a mitotic figure is and what's a lookalike. So we need to simply evaluate the performance with statistic metrics. Of course, you can also just visualize the text image, but you need metrics to see the performance. And the metrics will depend on whether this is a classification task, an object detection task, or segmentation task, and they will be different. And I will go through the task for the classification object detection task, and I will not talk about segmentation for purposes of time. So classification, I think most of you are very familiar with the metrics. So based on the prediction by the algorithm and the ground truth that we as pathologists determined or gave to the image, you can define whether this is a true positive, a false negative, a false positive, or a true positive detection. And with those metrics, you can then calculate a sensitivity and specificity and accuracy. And I think all of you do know those parameters, so I'm not going to go into details. But there are also some more complicated methods, and we have detailed those in our guidelines. So if you're interested, please take a look. We have a table with all the metrics. They're very interesting, but a little bit more complicated, so I won't have time to go and explain those. Right, so for object detection, so that is when you detect mitotic figures in an image, you don't have true negatives. You still have true positives, you still have false positives, and you still have false negatives, but you don't have true negatives, because everything else but those three instances would be negatives. And so your metrics would just be biased into the direction of having a high proportion of true negatives. So that would be 1 versus 1 million, for example. So that's not reasonable to use for object detection. And you still can calculate sensitivity. So that's this example. If you don't have true negatives, you can still calculate sensitivity, but it's called recall, generally for object detection. That's the same thing. You can't calculate, however, specificity. So what's usually done is to use precision, and precision tells you how many selected items are relevant. So those are selected items, and how many of those selected items are true ground truth items. So if you detect, 12 mitotic figures, and 6 of those are true mitotic figures based on your ground truth, you would have a precision of 50%. And then the combination of recall and precision, the harmonic mean, would be the F1 score, which is a little bit similar to the accuracy. Right, and again, average precision and mean average precision are metrics that can be used, but for details, you can look up our guideline. Okay, so the last and final step, and we not nearly close to that step for routine applications, is to think about how we can apply those algorithms for routine uses and at the end improve tumor prognostication. So as opposed to the manual approach where we have a pathologist to evaluate the tumor and give the diagnosis, we can now use an algorithm. As I said earlier, we want to increase reproducibility, ideally also accuracy, and especially for big labs, a big goal is to increase efficiency. And instead of using the fully algorithmic results, we actually propose to use the computer-assisted approach. So because we do know that algorithms have errors, and it's, at least up to now, it's not easy to realize the situations where your algorithm is going to fail. We propose that the pathologist takes over the case and ensures accuracy and ensures reliability of your prognostication, and therefore also can have the liability and reliability for diagnosis. So the idea behind this is that algorithms have advantages. So we want to use those advantages and assist pathologists, but algorithms have limitations, and those limitations need to be eliminated by a review of experts, of pathologists. So certainly, algorithm performance is going to depend on many aspects. And first of all, your performance of your algorithms, which you can evaluate with metrics. And you need to make sure that your data set is representative of that intended use for your lab. You can also differ the sensitivity versus specificity or precision trade-off of your algorithm, depending on what you want for your specific task. And this needs to be considered. You need to have easy handling of the software. And this is also a step that you still need to work on. How can pathologists interact with the software? How can pathologists correct errors in a sufficient and easy way? So we need to modify software so that they can interact, or we can interact with. Right, and then we need to have studies, or need to have more information about how pathologists can actually, or if pathologists can detect errors, and if the computer-assisted approach is a good approach. So the first question is especially regarding the efficiency. So how much review do we need? Do we need pathologists to review each single detection? So for example, if you have a metastatic figure algorithm, do pathologists need to review each annotation, or does pathologists just need to confirm a couple, and if they're happy, they can accept all of the detections? This, of course, obviously will have an effect on efficiency of your workflow. We need to work on transparency of algorithms. So how can we display results of the algorithm in order that pathologists can understand the detections most ideally, although we know it's a black box. And we need to understand how the confirmation bias is acting on us pathologists. And we need to get familiar with software and customize with software so that we are not influenced either in a negative or in a positive way. So what we recommend is generally to use computer-assisted approaches. We recommend that the algorithm should be displayed with each intermediate step. So for example, if you analyze an image from metastatic figures, show each metastatic figure as an overlay on the whole set image. And then you can, in the second step, display a heat map and propose a hotspot location, for example. But you should be able to review each individual step as a pathologist. So this is important for understanding the algorithm and verifying the results. So we need to have studies, and each lab actually should validate the AI workflow. So because we do know that algorithms can have problems with different data. So if your algorithm is trained in lab A, you cannot just use it in lab B. So we need to verify that your algorithm is working in lab B. And we still need much more publications on how algorithms work and how they can assist us as pathologists. And this was also a comment in the chat earlier, so I added this point, open source and open data. So we are currently in a state where we, as researchers develop algorithms, we modifying algorithms, improving algorithms, find different opportunities how they can assist us. We're not at a state where they are used routinely, not yet quite. So we're still trying to find our best solutions. And for this, we need open data, open sources. So there's no use of a publication where someone develops an algorithm, doesn't tell us how they developed us, and just say, okay, the algorithm works perfectly, outperformed any pathologist, and I have this algorithm. So we don't really need those publications. We need publications that talk about which method is the best for training the algorithm, and ideally also publishing the code for the algorithm. We need publications on open data so that everyone can use this data for training and evaluating. So different research groups can compare the robustness of the algorithm, whether their algorithm trained with lab A can work on lab B, for example. So we need those publications. For this, we need open access. And I don't think this is going to limit the individual researcher. This is going to expand the opportunities for everyone. And obviously, in the long term, we need to evaluate whether our approaches are helpful on prognostication and also have an effect on efficiency and for big labs especially. So if we can offer prognostication to a wider range of patients. And last but not least, you need to revalidate if you change your workflow. So if you get a new scanner, you need to revalidate your algorithm, because this is going to have potentially a big influence on your performance. Okay, so I think we still have time, right? So I will give you two examples, one about mitotic count. This is basically the results from our research group from different studies. So this is specific to veterinary medicine, and then just quickly go through a second example from human medicine. So mitotic count is a very popular topic, and we just have talked about how difficult it is to do a accurate mitotic count. So it's very promising to use algorithms for the different steps for detecting hotspot regions and for classifying or detecting individual mitotic figures. And we have actually evaluated both. So we developed an algorithm. This is an algorithm for cutaneous mast cell tumors. The dark green colors spots are the true mitotic figures, whereas the light green are lookalikes. So we decided to also display the lookalikes just for pathologists to better understand the algorithm and where they and how the distinguishing between those two worked. But this is also something that needs to be researched, whether this is good to use to visualize the lookalikes, or whether this is biasing the pathologist or not. Anyway, so the dark green spots compared to the ground truth had an F1 score of 0.82, which is actually pretty high and not reached by many pathologists. So we can train an algorithm with very high performance on this data set for this domain. So for lab A with scanner A, with staining procedure A. So this was very high. But we also have compared this to some other smaller available data sets, also from human medicine, and we did see that the performance does drop quite significantly, and especially if the scanner is different. And we're currently investigating approaches and performing a challenge to increase or find methods for improving the algorithm performance and reducing the domain shift. And then we also compared whether algorithms are able to detect hotspots. So we invested the time to annotate data sets for whole set images, which was pretty time consuming. So we had 23, I think it was, whole set images of mast cell tumors and annotated each mitotic figure in the whole set image. So we were able to actually calculate the mitotic density and visualize where the hotspots are. And when we correlated the mitotic count prediction from the algorithm compared to the true mitotic density based on our ground truth, we could see that we have a very high correlation. So we are assuming that algorithms are pretty good in actually detecting the mitotic density in the tumor section. The advantage of algorithms is that they can analyze entire whole set images in a very systematic way. So they can analyze and go through the entire image, whereas we don't have the time to do that. We just pick certain images that look promising, and then probably after looking at a few images, we just pick the one that we like. And so we won't ever look at each image at high magnification to find the mitotic figures, and the algorithm does. So this is, I did show this graph in the mitotic count presentation earlier. And I did show this in the context that pathologists have some difficulties in detecting hotspots. So this is a forest plot, and you can see the percentage of counts or cases being within the upper 50% of the mitotic count distribution or being in the upper 25 mitotic count distribution. Especially in this right image, pathologists were not always getting the hotspots, right? So it's more or less lucky if you get the highest 25%. Whereas algorithms generally were much better than pathologists. So they analyze entire images. They see each section, so they can calculate the heat maps much better than we can. And so this is a recent study that we performed, and I also mentioned this in the previous talk. You can access this publication as a pre-published manuscript. We're currently having this manuscript under review in a journal. But anyway, so with this study, we tried to evaluate different ways how algorithms could potentially assist us, and which is the best way to support pathologists. So we had 3 stages. Stage 1 is the routine mitotic count, so that pathologists did not have. It was 23 pathologists, by the way, and 50 mast cell tumor cases. And the algorithms, we used the same algorithm that I previously described. So this is the same algorithm that we previously developed and now tested on different images. So it's still the same lab, still the same scanner, but different cases. So it's an independent data set. Stage 1 would be the routine mitotic count. No help for pathologists. They have to look for the mitotic count hotspot, and they have to classify the mitotic figures. Stage 2 was we were using the algorithm, especially the heat map, and pathologists were proposed a hotspot location, and they had to count the mitotic figures within that location of the tumor. And stage 3, they were shown the same area, but also there were visualization of the mitotic figures that algorithm was proposing. So the limitation of the study certainly is that pathologists couldn't completely interact with the software, so they weren't able to change location, for example, because we needed that to be fixed for comparison reasons. But this is certainly something that we need to elaborate on, and how pathologists can change the software predictions and correct errors. So, right, so I'm just going to show one graph, and so I'm limiting the information because I'm giving a talk for the ECVP conference next week on this topic, and also we'll have a talk for the ACVP on AI softwares for AI. And so for anyone who's interested in more details on this topic, should join those presentations or read the publication as linked here. So anyway, so this graph is just comparing stage 2 and stage 3. So pathologists had the same tumor location, and the tumor location, by the way, was generally higher than the ones that the pathologists selected. So algorithms also in this study had higher capability to detect hotspots. And when pathologists did evaluate the same area, they had also higher consistency. So it's, eliminating the variability of area selection is certainly something beneficial. So, but when pathologists evaluated the same area without visualization of mitotic figures and with visualization of mitotic figures, the green spots, we can see that there was generally an improvement. And the red spots you did see for the mitotic count presentation already. So generally pathologists have a wide range of recall versus precision. So some pathologists have a high precision but low recall, and some pathologists have a high recall but low precision. And this was true, and this is just how humans work. But independent of that, pathologists did increase generally their performance when they had visualization of mitotic figures. So, and especially the recall improved, meaning that pathologists did not overlook that many mitotic figures anymore. So overlooking mitotic figures apparently seems to be a huge problem. And when algorithms visualize them, or visualize at least potential candidates, and pathologists can think whether they want to count or not, this is increasing the recall by a lot. So algorithms, at least in this study, were useful to, we need more studies to evaluate how they are applied ideally, and how this has an effect on efficiency and so forth. Right, so this is a study, as I mentioned, from human pathology. So this is not from our research group. You can find or read details via this link. And they evaluated the influence of algorithms for detecting lymph node metastasis. So this is again human breast cancer. And you earlier did see an image, with a very obvious lymph node metastasis, but there's also cases where you have micrometastasis, and those are not very easily seen on the overview image. So for example, some of you find the lymph node metastasis in this image. So this again is a canine case. It's not from that study, but it's the same thing. So actually, it's down here. And the aim of the algorithm is just to highlight those structures so pathologists can quickly see them and don't have the potential to overlook. And this algorithm wasn't too helpful for macrometastasis. So when pathologists can easily see the metastasis on low magnification, there's no benefit of the algorithm because we can already see them. But especially for micrometastasis, it was significantly, so compared to the unassisted approach, the assisted approach was significantly increasing your sensitivity. So again, we don't overlook structures that are small and not obvious to us at a specific magnification. And again, because pathologists didn't have to go look for it, they were also able to increase the time investment significantly. And they've considered the lymph node metastasis to be more obvious when they were highlighted by the algorithm, which seems very, very reasonable. Okay, so that's the presentation. I think it's probably only answering very few questions, and we need a lot of more studies to develop this project and these topics. So hopefully we can also improve our guidelines in the future with many studies. And I want to thank the Davis-Thompson Foundation for hosting this webinar. Of course, also I want to thank the American College of Veterinary Pathology for co-hosting. And I want to thank the co-authors of this guideline and the co-authors of all the studies that I was able to present. And I hope that this information can be of value for you. Thank you very much.